Okay, so in this video, my goal is to give you a vector description of things. After all, quantities in physics are vector quantities, so you surely can give a vector description. My description of tangential and radial accelerations, and a lot of it's been a little squishy on some of the vector properties. I've been focusing on the scalar factors and just kind of um, really the only place where vector stuff even came up was with using the Pythagorean theorem to get the magnitude of the acceleration. And but that even there, I just kind of said because it's a right triangle, we know what to do without actually writing down vectors. So in this video, I want to be a little bit more careful. So to do that, what I first want to do is kind of go back and forth and develop the relationship between polar and radial coordinates a little bit. And let's kind of think about things a little bit harder than we have been. So let me change colors. I think I've got a black. Hopefully this works. Okay, so let's pick a point here in the plane. Now, that's a point. It's just a place in the plane. And the way that you describe its position does not matter. I mean, as long as it's consistent, as long as you don't screw it up. So there's not one way to do that. And in fact, I've kind of indicated two different ways. I've drawn the usual XY coordinate system, but I've also drawn these concentric circles. Both are fine. You can do other things. There are an infinite number of coordinates. It does not matter, although most of the time you're given a choice between a cookie and a kick in the head. Doing something crazy is just a kick in the head. There's no benefit because the actual answer, the physical information won't care about the choices you make. Okay, so we can describe this point in two different ways. We can describe this point as either being so much in the x direction and so much in the y direction. That's okay. So I could give it an ordered pair x, y. Or I could kind of ask, all right, which of these concentric circles does it live on? What's the radius of that concentric circle? Little r. And I could also then say, what angle do I have here? So I can also describe the same point using r and theta to parameterize it. And that's okay. It's a point in two dimensions. You always have to specify 2 bits of information and no more than that. 2 bits of information are enough to specify the point in the plane. Okay, so that's fine. So now that we have these two descriptions of the same point, we need to come up with a dictionary between them. And that's pretty easy. Just think back to your unit circle days. You know how to relate x and y on a unit circle to theta. And a unit circle is radius 1, but if you had a different radius, you just rescale it. So what we learn, or if you don't like that, if you don't remember, you would turn this into a triangle, and you would say, okay, theta is here. Clean up my diagram a little bit. Theta is here. So you'd say cosine of theta is going to determine the x coordinate, and sine of theta is going to determine the y coordinate. So we're going to say that x equals r cosine of theta, and y equals r sine of theta. Just a comment, people use r all the time in physics and science and math. So it's easy to get confused. It's easy to kind of equivocate different meanings of r, and in one problem you can have different position vectors. This semester I'm helping with teach dynamics, and right now we're doing we're talking about rotations of rigid bodies, and I just had a problem where it was like a hinge going to some sort of a joint, going to some sort of other joint, hooked to a hinge or a rod that was rotating at some frequency. And as this rod rotates, it makes the others all wiggle and jiggle in relationship. And you have all kinds of radial directions, right? You have a radial kind of a rotation going on here, a rotation going on here, a rotation going on there. It's easy to get confused about what you mean. So you've got to be really careful with some of this stuff. To help me, one of the things I like to do is if I have a radial direction, which is constant and unchanging, I will make it a capital R. Or sometimes I call it capital L for length, but usually capital R. If I have a radial coordinate which can change, I like to make them lowercase r's. And that way, visually, I just know that if I have lowercase r's, oh, heads up, there's probably some calculus involved, or things can be changing in time. Okay, so that's one thing. You can go back the other way, and you can show that r is equal to the square root of x squared plus y squared, using the fact that sine squared plus cosine squared is 1. And similarly, you can find that tan theta is equal to y over x. Okay, so you can go back and forth using these relationships. So that's how you go back and forth between coordinates, the coordinate x and y. Now let's talk about vectors. All right, so we introduced basis vectors x hat and y hat. Remember, x and y, there's nothing special about x and y coordinates. They're one of an infinite number of choices you can make. So that means that even though we used x hat and y hat, we didn't have to use x hat and y hat. We could use any two so-called linearly independent basis vectors. They don't even have to be perpendicular, although you're really choosing to kick in the head if you do something other, if you don't do that. So what we want is to come up with the analog of unit vectors, but not referencing x and y. Instead, let's have them reference r and theta. So let's think about this. The original way I defined x hat was a vector, a unit vector, in direction of increasing x. Where x is the coordinate. So the x hat unit vector, so the unit vector associated with the coordinate x, is a unit vector which points in the direction of increasing x, and similarly for y. Well, then that kind of tells me what I want to do. I want to think about r hat and theta hat as unit vectors, and I want them to be unit vectors which point in the direction of increasing r and increasing theta. So I want to say that r hat is a unit vector in direction of increasing r, the radial, or the radius, or the radial coordinate. And similarly, theta hat will be a unit vector in the direction of increasing theta. So if you think about this, let me kind of clean up my picture a little bit here. If I have a coordinate system like this, and I superimpose a circle, so I have a point right here, and I superimpose a circle, if you're standing right here at this point, r is the distance to the origin, and if you increase r, that's a step radially away from the origin. So r hat, when you're standing right here, r hat points outwards. I don't know. But look what happens if you're over here. If I'm standing here, a direction of increasing r would move me that way. And now we kind of see the difference between x hat, y hat versus r hat and theta hat. They're all perfectly good basis vectors. The thing that's special about x hat and y hat is that they're constant in the plane. They're the same. They don't, as you move around from point to point to point in the plane, they don't change. That's not true for other choices of basis vectors. R hat, as we see here, when I stand in the first quadrant, it kind of points up and to the right. When I'm in the second quadrant, it's kind of to the left, up and to the left. So r hat changes. It's not a constant vector. So people don't write the fact that r hat depends upon theta, the angle, but in fact it does, because visually you see that as you move around a unit circle or around any circle, the direction that the radial unit vector points must change. What about theta hat? What's the direction of increasing angle? Well, if I'm standing right here, say along the x-axis, increasing the angle kind of moves me upwards. So that means theta hat points upwards. And if I'm standing right here on my dot, increasing the angle moves me kind of on the diagonal. And what I conclude is that theta hat always points tangent to the circle. And it changes, it tips as you go around. So theta hat points tangent to the circle, r hat points perpendicular to the circle. And that makes sense because a circle is a curve of fixed radius. So all along a circle, the radius can't change. So r hat has to be not that way, has to be perpendicular, and which means theta hat must be along in that direction. Okay, so those are kind of conceptually what we mean by x hat and y hat, and then r hat and theta hat. We're going to come up with some explicit formulas relating things here. Let's go back to that point that we started with. And we said it could be described either by xy or r and theta. And those are fine descriptions of it as a point. On the other hand, if I prefer, I could think about this point as defining a vector. Just like we've said that positions in space could define vectors going back to the origin, or from the origin to the point, actually. So if I want to do that, and the vector we usually call, right, the name we would give for that vector is r vector. A lot of r's. Remember I was saying there are a lot of r's. You got to be careful. So r vector points, or goes from the origin to the point, and it points radially away from the origin. So it points radially, and it has length, or it extends from the origin to the point. Huh. Well, that means that its magnitude must be the radial coordinate. So the magnitude of r vector must simply be the radial coordinate, and the direction associated with r vector must be the radial unit vector. So when I pull those facts together, it tells me that I can say that r vector equals r coordinate times the unit vector r hat. Because think, if it's not obvious, think about it. What's the magnitude of this thing? Well, r hat has length 1. R is just a scalar, so that has magnitude r. So the right-hand side has magnitude r. So that's the second fact. And it points radially away. So it must be r hat. So that's our formula for r in terms of polar coordinates and polar unit vectors. On the other hand, we have the following relationship. We know that must equal, just looking at it, it must equal r cosine theta x hat plus r sine theta y hat, because it has to equal x in the x direction and y in the y direction. And then rearranging that allows me to conclude that there's a relationship, a formula, relating r hat and x hat and y hat. I learned that it must be true that r hat equals cosine theta x hat plus sine theta y hat. So remember, I said there's that any vector, any basis vector will do, and that means that you should be able to convert one into another, no problem. Just an observation here. Let's take a derivative of r hat with respect to theta. I know it looks a little, it maybe feels a little weird because it's a vector, but you just do calculus. And remember, x hat and y hats are constant, so they don't change. This is simply going to be minus sine theta x hat plus cosine theta y hat. Take a second and do the calculus there. So remember that. I think I'll just leave that there. Okay, just leave that there for a minute. Okay, so what we found was that there's a relationship. We had that r hat could be written as cosine theta x hat plus sine theta y hat. Furthermore, and r hat points radially away from the origin. That's fine. What about, so that's the radial unit vector. What about the angular unit vector? So that vector has to be tangent to the circle, And let's kind of figure it out by feeling our way through it. Let's imagine the angle 0. It's like if you're right here at 0 degrees, so when theta is 0, theta hat should be y hat. Let's go choose a nicer point. So note, at theta equals 0, theta hat equals y hat. At theta equals 90 degrees, or pi over 2, so if you get up here to 90 degrees, theta hat will point to the left. So that would be theta hat equals negative x hat. And it goes around, and everything's periodic because you add 2 pi to all these angles, it's the same story. So we expect, look modeled on our formula for r hat, and seeing that it depends upon theta as functions in there. Then what I expect is some sort of functions. It's got to be periodic in 2 pi, which means it's built out of sines and cosines of theta. And when theta is 0, the x component has to go away, and the y component has to be 1. And when theta is not pi over 2, the x component is negative 1, and the y component is 0. So if I was making a guess, which turns out to be a good guess, you would guess that theta hat is equal to negative sine of theta x hat plus cosine of theta y hat. You can check. If you plug in theta equals 0, first term goes away, and you just get y hat. On the other hand, if you plug in 90 degrees at pi over 2, you get negative x hat plus 0. So it checks. And then I want to draw your attention to this. That's just what we found before. What we found is that the derivative of the radial unit vector with respect to the angle, gives you the angular unit vector. Does that make sense? So I'll write that out. Well, let me write this up here. I have that theta hat is going to be minus sine theta x hat plus cosine theta y hat. And what we found was that the derivative of r hat with respect to the coordinate theta is equal to the angular unit vector. Look, here's kind of a way to think of it. It's a unit vector. Right? So let me draw, if I have a point here. Right? So at this point, r hat points radially away. If you were to increase the angle a little bit, what could happen to this guy? Well, there are 2 ways you might imagine that you could change this vector. You might think it stretches, or you might think it tips. However, it always has to be a unit vector. That means it can't elongate. See, the only thing it can do is tip and rotate. But that means that the change, as you increase the angle, the change in the unit vector has to be in the perpendicular transverse direction, which would be theta hat. So that's one way to think of it. It turns out, and you can verify this by taking another derivative, that d theta hat d theta, or can't tell if that's hail or heavy rain. Anyway, it is what it is. The derivative of theta hat with respect to theta, just quickly do that. That's going to be minus sine theta x hat plus, sorry, minus cosine theta x hat minus y hat. That's actually equal to minus r hat. So that just comes out from the calculus, or if you draw the triangles, you can figure that out. Okay, these are the facts we need right here. All right, so we know, I'll write these down here. We know that the derivative on r hat with respect to theta is theta hat. We know that the derivative on theta hat with respect to theta equals minus r hat. Incidentally, the derivative of the unit vectors with respect to the radius is 0. That is an artifact of this choice of coordinates. If you chose just totally random coordinates, everything depends upon everything, and it's a complete circus. But you know, you can, the math is known, you can work it out, but there's usually very little benefit in doing that. And the other thing I wanted to say was that omega was defined to be the time derivative of theta, and alpha is the second derivative of theta. Okay, from our last video. So let's box those things in. We're going to use those. Okay, kind of gone through the geometry. We've gone through the coordinates. I've reminded you of the things we knew last time. What I want to do is write down a position vector in the plane, take its derivative. That's going to be the velocity. Let's work it out using these properties, and we're going to rewrite it in terms of a bit of the velocity which is along the circle and a bit of the velocity which is maybe perpendicular to a circle. And then we'll take another derivative, and then we'll get an acceleration which is along the circle and a bit which is radial away from the circle. And then we'll specialize to the case where you have circular motion so that the radius stays constant, and then we'll get back to centripetal and tangential accelerations formulas that we've seen before. Okay, so for a point in the plane, we found that position vector was r times r hat. And then if I wanted to write down the velocity vector, that would be the coordinate derivative, r hat, plus r times the derivative on the unit vector. Remember, it looks a little funny to take a derivative of a unit vector, but these are not constants. So if this was x hat, it would be 0, but it's not. It has, we know, because we know that they depend upon angles. And then we're going to use the chain rule to write this. Basically, we're going to write r hat dot as dr hat d theta times theta dot. And similarly, theta hat dot is going to be d theta hat d theta times theta dot, using the chain rule. So when I do that on this one, that's going to be theta hat times omega. Okay. Okay, remember that. Okay. Now let's rewrite the acceleration. The acceleration is just the derivative on the velocity. Just go through it. Product rule everywhere. There's no magic. It's just hold on tight. It's going to be r double dot times r hat plus r dot r hat dot plus r dot omega theta hat plus r omega dot theta hat plus r omega theta hat dot. Whew. And now we're going to use these properties to kind of re-express things. And I can write this. So let's see, where are we going to have radial unit vectors? I'm going to have a radial unit vector here, and I'm going to have a radial unit vector here. And this is going to give me r double dot. And this is going to give me minus r omega squared times r hat plus plus in the angular direction, I'm going to have something from here, and that's going to give me an omega times r dot, which is this doubles this one up, and then I have this one. I'm going to get r alpha omega dot plus 2r dot omega. Okay. Whew, what a mess. But that is the velocity. This is the same formula we've been seeing, or well, sort of. Okay, so let's go through this. So first of all, if there's no rotation, omega and alpha are 0, and this just becomes, so no rotation, and it just becomes r double dot times r hat. It just looks like the usual acceleration in the radial direction, linear acceleration in the radial direction. Okay, so that's easy to understand. What if we had uniform circular motion? What if we had circular motion circular motion? So that means that r is a constant. Just call it capital R. So that would mean this term goes away, and it would mean this term goes away because the time derivative would kill it. And I would get in the radial direction, I would have, I would have my acceleration would be minus r times omega squared times r hat plus, and if it's uniform circular motion, then alpha is 0. So you would get an if you have uniform circular motion, well, that's good because we're expecting the answer to point in the negative radial direction. So that makes sense. We just have to verify that that's the centripetal acceleration formula. Well, to do that, let's imagine we have uniform circular motion. In that case, going up to the velocity, the first term is 0 because r is be constant, and I would get that the velocity is r omega theta hat. So the magnitude of the velocity, or the component of the velocity tangent to the circle would be r omega. So this, in fact, would say that the acceleration radial has a magnitude of v squared over r when you use this term to identify the velocity. So this is just the centripetal acceleration. So we learned that this is the centripetal acceleration. This is the usual sort of acceleration we would expect. So this is the usual linear piece. This is centripetal. Petal, I think. This one points in the theta hat direction, so that's tangent to the circle. And this term is r times alpha in the tangent direction. Well, that's nothing other than what we called a tan. That's the tangential acceleration. And then this term is the weird one. This term is the Coriolis. Coriolis. I can't spell it. Coriolis term. You spell it however you want. All right. And what this term is, what this term says is that if there's something moving, how do I describe this? Well, that's not even quite the right way to say it, but it's the precursor to the thing. Basically, this is sort of it's an effective acceleration along the circle caused by motion. I don't quite want to go into what is the Coriolis effect in detail, but it's just it looks like a sideways acceleration caused by the motions. And if you wanted to, depending on your reference frame, it will look like there must be a kind of a sideways force which causes that. And it's not really there, but it would sort of feel that way. Yeah, so all right. So this expression is what we have, and I've shown how each of the pieces of this reproduce the things we've already seen. So hopefully this all makes sense. I reiterate, as I said in the last video, this sort of mathematical description is not something that you're going to be responsible for this semester, but this is the way that dynamics class will go. Problems with dynamics are written in this language. So, okay, that's all for this video.